Just a few more odds and ends about the derivative as a function before we wrap this section up. I have a definition here. A function f is differentiable at x equals a if f prime of a exists. So the last time we were together in Zoom, we took a look at the function f of x equals x cubed. And then after a little bit of pain and suffering, we found that f prime of x was equal to 3x squared. All right, so any number that we can plug into f prime of x and get an answer, that's going to mean the function, the original function, is differentiable there. So this is x squared. We can plug in any number that we want, but let's just say 2. So f prime of 2, when I plug this in, obviously I can square any number I want, and I'm going to get an answer of 12 here. So we would say that the original function x cubed is differentiable at x equals 2 because we can get an answer from its derivative. So f is differentiable at x equals 2. Okay, turns out for this particular function, f is differentiable anywhere. I can plug in any x value that I want. Okay, but we also did a derivative for f of x equals root x minus 3. And again, after some pain and suffering, we got the derivative to be this thing. 1 over 2 root x minus 3. So for this one, I could plug in lots of numbers. I could plug in x equals 4 and x equals 10, and I can get answers out of the derivative that exist. One that I can't plug in would be, for example, 3. If I plug in x equals 3. So this is a point that's actually defined on the original function, but when I plug it in to the derivative, I get something that does not exist. So we would say that this f of x here, this root function, is not differentiable at x equals 3. It's a not differentiable at x equals 3. In general, if a function is differentiable at every value of x, like x cubed appears to be, then we just say that that function is differentiable. We don't specify a particular x coordinate. Graphically, it's pretty easy to tell where a function is differentiable or not. A function will not be differentiable at cusps or corners. So a cusp would be something like this, where there's some little curvature to it. And you can imagine that the derivative doesn't exist at that point where there's a cusp, because if you try to draw the tangent line, you could draw this tangent line, you could draw this tangent line. There's kind of an infinite number of tangent lines at that point. So there's no function value for the derivative there, no one output for that input at the cusp. Likewise, if we had the absolute value graph, we know that that one is not going to have a tangent line at that point at the bottom. All right. Also, at discontinuities, any place a function is discontinuous, it's not going to have a derivative there. So we won't have it being differentiable at discontinuities. Any place where the tangent line is vertical, these are sort of rare, but this would be a function like cube root of x, where it comes up and just for a brief moment, it goes completely vertical with its tangent line. And we know that vertical lines have undefined slope. So if the slope of the tangent line is undefined, that means the derivative is undefined. There are a few other kinds of funky functions. Your book goes over one that are sort of created by creative mathematicians trying to come up with a function that is not differentiable at a given point. We're not going to worry about those, mainly just the first 3 bullets. So let's see if we can master that bullet list of places where a function is not differentiable just by looking at its graph. So we're going to be looking for cusps and corners, discontinuities, or vertical tangent lines. All right, so I see a couple of discontinuities here. I see one at -2. Okay, so we're not going to have a tangent line there, so our function derivative is not going to be defined. So we're going to say it's not differentiable at x equals -2, comma, because I've got a few more spots on this graph. I see another discontinuity, an infinite discontinuity at, we're going to have to guess here, x equals 6 looks like the most likely candidate. All right, so we're going to say it's not defined there, so it can't have a derivative there. So we're going to say at x equals 6. And then I've got one more spot that I see where the derivative is not going to exist, and that is a cusp. And I've got it over here at x equals 2. All right, so we're going to say at x equals 2, we've got a cusp, and we know that the derivative is not defined there. I don't see any places on this graph where the tangent line goes completely vertical, but you might have one in your homework, so be on the lookout for it. One last thing is this little theorem that tells us that if a function is differentiable at a point x equals a, then f is also continuous at x equals a. So if you remember a while back, we used that limit definition of continuity. We said if the limit at a point was equal to the function value at the point, then the function was continuous at that point. We can circumvent that if we happen to know that the function is differentiable at that point. So we know that if we have some function that's differentiable, we get for free that it's also continuous. The implication does not go the other way. We can't say that if a function is continuous at a point, that it's then differentiable. So we'll say we can't do that. And a counterexample that would illustrate that would be the absolute value function. We are certainly continuous at the origin where we have that V spot, but we know we're not differentiable there. Right. So if you know differentiable, you get continuity, not the other way around. In fact, there was a mathematician called Weierstrass who famously came up with a function that is continuous everywhere, but differentiable nowhere. So let me write his name down, Weierstrass. So he came up with a function, and it's a weird one. You can look it up, just Google continuous everywhere, but differentiable nowhere. It's kind of a crazy looking function.